last chance here. Okay. Almost everybody says that it is phosphorus P. And that would be the correct answer. Now again, how do we know that? Well, we have to, again, remember the differences between periods and groups. Periods would be the horizontal rows. Group would be the vertical columns. So if I piece it together like a game of Battleship, group 3, row 3, column 15, that gets you right on phosphorus P. Now, for the two of you that said arsenic, not bad thinking, but you forgot one really important thing. This top row does exist. There's only 2 elements in it, but it does exist. So you don't just count the 3rd row that you see. You have to start at the top. All right, let's try another one. Write the symbol for the transition metal in period 4, group 4. And go. Give you 1 minute this time. About 10 seconds. All right, got everybody? All right, better this time. 17 of you are correct. Period 4 would be row number 4. Group 4, column 4. Again, you just kind of follow it along. That would be titanium Ti. All right, one more here. Write the elemental symbol for either of the metalloids in period 5. So there are 2 possible correct answers here. I just need one of them. About 10 more seconds. All right, let's see how we did. All right, a little bit more spread here. The 2 correct answers. Remember, the metalloids are the ones that straddle that zigzag line that goes from between the metals and the nonmetals. And so in period 5, that zigzag line is straddled by antimony, SB, on the left, and tellurium, TE, on the right. So it appears most of you got it. Not exactly sure why this tellurium wasn't marked as correct. Maybe there's an extra space in there somewhere or something like that. No matter, the grades for participation, not accuracy anyway. All right, so any questions about that kind of stuff from the periodic table? Okay, so let me give you a couple of reminders before we move on to the next thing. First of all, your scores for the elements proficiency were recorded on Monday. If you have a grade other than 10 in that column, you need to take it again. So either make arrangements with your lab instructor or with me, through my office hours or by appointment, to come take that proficiency and get that 0 turned into an 8 so that you can move on. Second reminder is that our next proficiency, the ions proficiency, is this coming Friday. So we'll do that at the very beginning of class here. Make sure that you're prepared for that when you walk in the door. Third thing is this, that periodic table mystery activity that we did at the end of class. The key for that activity has been posted in Top Hat, so you should be able to look and compare what you did. And if you have any questions about, how I came up with my answers versus what you came up with, let me know, and I'll be glad to walk you through what the process was. But we're moving on to the next thing right now. And the next thing right now is average atomic mass. Now, you had to tackle average atomic mass as part of one of your more recent post-lecture activities, where we kind of asked you what was the difference between average atomic mass and mass number. Average atomic mass comes about as a result of calculation. In particular, what we are looking at is the comparison of the mass of a particular isotope relative to its abundance. So the more prominent an isotope is, the more of an effect it's going to have on the average mass of the substance. Now, again, this is a weighted average. So how do we determine what the actual average is? Well, we have to do some math. And the math that we do is this. We take the atomic mass and we multiply it by its percent abundance. And after we do all of that multiplication, we add them all together to give us the weighted average. So that is our ultimate goal as far as average atomic masses are concerned, is we're going to use these percent abundances and these isotopic masses to generate what will eventually go onto the periodic table as the average mass of that particular isotope. Now, why do we want to concern ourselves with that? Because more often than not, when we are dealing with reactions, we're not going to be dealing with individual isotopes. We're not going to be dealing with individual atoms. We're going to be dealing with large numbers of those atoms. And so even for an isotope that has a relatively low abundance, I mean, 0.2696% is not very much. One out of every 250 atoms of neon is that particular isotope. And yet, if I have a sample that has millions upon millions of atoms in it, you're going to know that some of them are neon 21. So how do we account for that? That's where the average mass comes in. And that's why the periodic table reports those average masses. Because when we do chemistry in terms of chemical reactions, even the smallest abundances are going to be somewhat prominent. They're going to have some effect on our overall mass. And so that's why we account for them. So let's do a practice problem of this kind. Again, focusing on the neon here. So like I said, the calculation method that we're going to use is a multiplication effect. We're going to multiply these by each other, or I'm sorry, we're going to multiply the masses by their abundances, and then we're going to add them together. So 19.9924 times 90.4838 to 6 significant figures would be 1,808.99 AMUs. $20.9940 times 0.2696 to 4 significant figures would be 5.660 AMUs. 21.9914 times 9.2465 to 5 significant figures would be 203.34 AMU. I add all of these together, 1808.99 plus 5.660 plus 203.34. And I get 2017.99 AMUs. Now, before we start reporting that as the actual mass, you should recognize something. How do I get an average of 2,000 and change from 3 numbers that barely clear 20? The answer is you don't. Remember, these are percentages. We've already multiplied by 100 to get these percentages. So to give us a number that makes sense, the last step that we have to do is divide them by 100. And when we divide it by 100, we get 20.1799 AMUs. And if you look at the periodic table for neon, 20.18 is what is reported here. On this table, 20.18. On that one, 20.1798. So you can see we're in pretty good agreement there. So that's what we have to do to get those weighted averages, to get those numbers on the periodic table. It's not a matter of a single isotope It's a matter of a combination of all of the isotopes with their relative abundances kind of baked into the calculation. And if I don't take that into consideration, I don't end up with the correct answer. Because again, if I did just a regular average of these three isotopes, I'd end up with a number around 21. And that's a far cry from this. There's a lot of error in that estimation by taking just a simple average instead of the weighted average. We need the weighted average because it takes into account how much of each of those isotopes there actually are. All right, any questions about this particular example? All right, so I want you to try this one yourself here. We know copper to exist in nature as two different isotopes. Copper 63, which is about 69.17%, and copper 65, which represents all of the rest. So that'd be 30.83%. The question I have for you is, what is its average atomic mass? So take a few minutes, give you a few minutes to work, try to calculate it. I'll come around and see how you're doing. And then we'll go through the answer together at the very end. So give you about 3 minutes to at least get yourself organized and try to figure out the answer. So the important thing to remember here, the most fundamental mistake that you can make is just to ignore the percentages. and just say, I've got two numbers here, let me add them up and divide by 2, that's my answer. Because if you do that, you're not going to get the correct answer. The only time that ever works is if the 2 isotopes or the 3 isotopes are all present exactly equal to each other, which that's almost never the case. So what we have to do is we have to set up our arithmetic calculation using the percents. So 62.9296 times 69.17%. That gives us to 4 significant figures. $43.53. And then we have 64.9278 AMUs times 30.83%. And the 4 significant figures, that one is 2002. If I add those together, I get 63.55. And after I divide by 100, I get 63.55 AMUs. Which again, if you look at the periodic table, that should be pretty close to the value that you see. Give or take, a couple on that last significant digit, depending upon how much rounding has been done. Now, for some of you, as I was walking around, I noticed that you already converted the percents into decimals, and that's fine. You can do that. The reason I skipped that step is just because it's too easy to forget. And if you forget to do it, when you get down to the bottom here, you get a number that you know doesn't make sense. And that should be kind of the reminder, oh yeah, I need to divide by 100. All right, any questions? So let's talk about then some applications of this. Why do we care about average atomic masses in the first place? Well, because what they can do for us is they can allow us to determine not just the mass of the individual atom or the cluster of atoms. They can give us ideas about how much a molecule weighs as well. All I need to do is add together the atomic mass for each element multiplied by the number of elements that are in that particular formula. So if I want to find the mass of sulfur dioxide, I take the mass of 1 sulfur and the mass of 2 times the mass of oxygen, and that would give me the mass of sulfur dioxide. Now again, this is in atomic mass units, which is great if I'm looking at an individual molecule. But since I rarely do reaction chemistry with individual molecules, molecular mass is a great theoretical construct, but practically it doesn't do very much for us. What do we need to do instead? Well, we need to look a little bit more deeply. Same thing for formula mass. Now, the only difference between molecular mass and formula mass is just what we're defining. Technically speaking, formula mass is describing ionic compounds, because there aren't really truly molecules of ionic compounds, because ionic compounds exist in this massive crystalline structure But we can get the same kind of idea. If I have a formula unit of calcium chloride, I can see that there's one calcium in it that weighs 40.08, two chlorides that each weigh 35.45. If I put them all together, I get 110.98 as the total mass of that particular formula unit. I'll be honest with you, if you want to call it a molecule, I'm not going to argue with you on it. Technically not correct, technically not worth the argument. But again, since we're talking about just an individual cluster of atoms, not terribly practical for us either. What we need is something that is a little bit more practical, something that describes things on a more macroscopic scale, so that when we are dealing with millions and millions of atoms, of molecules, we don't have to worry about, okay, how many AMUs is this? How do I determine what an AMU is? My balance says grams. Well, that's where the chemical mold comes in. For the chemical mold, what we have is a systematically defined term for quantity. The mole is 6.022 times 10 to the 23rd objects. So when I say millions and millions, I'm not even being close to the true scale of the mole. We're talking literally millions of millions of millions to get to the quantity of a mole. What's useful for us, though, yes, the particle relationship is important, but in terms of what we can use in the lab, this is what really helps us. By definition, 1 mole was defined as being the exact number of particles in 12 grams of the carbon-12 isotope. That's how we came up with the definition of what the AMU was, because we looked at how much one atom of carbon-12 weighed. This is how we're also defining the mole. And so, since there is that parallel relationship between atomic mass units, grams, atoms, molecules, and moles, they all kind of tie together very nicely. There is a relationship between grams and AMUs. You're never going to need to know that. It's basically Avogadro's number flipped. It's a reciprocal. But it does give us, again, there's that relationship there. Understand, the gram is a defined unit as well. All of our units had to come from somewhere. This is where the gram comes from. Why that's important to us is because now we can start to tie in together the relationships between moles and particles, and eventually between AMUs and grams. They all kind of talk about the same thing. So here we reintroduce the idea of the conversion factor. So the end of chapter 1 was all about unit conversions. How do I convert from kilograms to grams? How do I convert from cubic centimeters to milliliters? How do I convert between grams and milliliters using density? Well, now we have, how do I know how many particles how many molecules, how many atoms are in a given substance. The mole helps us to relate the two. And so we have two conversion factors in play. Both of them dealing with Avogadro's number and 1 mole. So if I'm converting from molecules to moles, I would end up dividing by Avogadro's number. If I want to convert from particles to moles, I divide by Avogadro's number. So in one direction I multiply, in the other direction I divide. Just depends on what I'm doing. Before we do this sample exercise, I've been dancing around a point and I need to make it. Molar mass allows us to tie together what we just talked about with AMUs and average mass to put it on the mole scale. Because by definition, that carbon 12 was used to define the gram and the AMU. Notice that they have exactly the same value on the scales. So the atomic mass of gold was 196.97 AMUs. The molar mass of gold, the mass of 1 mole of gold atoms, 196.97 grams. Sulfur trioxide, we calculated the mass of the sulfur plus the 3 oxygens. We've gotten 80.062 AMUs. If we take the mass of 1 mole of sulfur trioxide molecules, it would weigh 80.062 grams. So while that calculation that we did using AMUs was really important, it got us to know what those values on the periodic table are. Understand that it means exactly the same thing in grams if we're talking about 1 mole of those substances. And so pretty much from this spot on, we're going to be talking about things in terms of grams, moles, grams per mole, and so on. Because when we do experiments in the laboratory, that's the scale that we work on. I'm not going to see any of you running down and trying to eliminate everything but one tiny little atom or molecule to do your chemical reaction. First of all, because it's impossible, and second, because it's impractical. But to see you walk over to a balance and take some sulfur and go, okay, I got 0.35 grams of sulfur. How much sulfur is that? Well, now I know that I can take that mass off the periodic table, figure out how many moles of sulfur are in that sample, and convert it to atoms of sulfur if I need to. That's where this definition really holds for us, because it allows us to make that relationship and it allows it to hold on. And so I'm going to introduce this particular table to us because in this table, we can do all of those calculations and all of those conversions that we've been talking about for the past 20 minutes or so here. So if I have a compound, using its molar mass, I can figure out how much it weighs. Or if I know how much I have, if I've weighed it, I can turn it around and figure out how many moles of it there are. If I know the number of moles, I can multiply by Avogadro's number to figure out how many molecules there are. Or if it's ionic compound, how many formula units. If I'm dealing with a compound, I can also use the chemical formula of that compound as a relationship between it and its component elements. So take, for example, that sulfur trioxide that we were looking at, SO3. Based on its chemical formula, I know that for every SO3, I get one S or 3 O's. So one SO3 gives me one sulfur, 3 oxygens. So if I know the number of moles of sulfur trioxide, I also know, well, it's got to have an equal number of moles of sulfur and 3 times as many moles of oxygen because of its formula. And from there, I can break it down into, okay, I've got that 1 mole of sulfur. How much of this compound is sulfur? I can do a calculation that leads me there. How many sulfur atoms are there? I can do a calculation that gives me moles of sulfur multiplied by Avogadro's number to give me the atoms. So think of this map here as an organizational tool to help you connect what calculations you are trying to do with the numbers that you need to find to do that calculation, to do that conversion. And so depending upon where you start and where you want to end, you can find the appropriate path that leads you there. And following the arrows, you know which calculations you need to do, what things you need to put in that unit conversion. So with all that being said, let's go back to this sample exercise here and try to tackle these calculations with that idea in mind. So we have silicon. In order to make silicon into computer chips, they have to be pure. They can contain no fewer than 3 times 10 to the negative 10th moles of phosphorus for every mole of silicon. What is that level of impurity expressed in atoms per mole of silicon? So starting with our given information, we have 3 times 10 to the negative 10th moles of phosphorus for every 1 mole of silicon. And where we want to go is we want to go to atoms of phosphorus for every mole of silicon. So we really just want to convert moles to atoms. If I jump ahead to that map, I can see to go from moles of an element to atoms of an element, I just need to multiply by Avogadro's number. The mole map tells me to do so that way. From a dimensional analysis standpoint, I can look at this and say, okay, I have moles of phosphorus in my numerator, so I need moles of phosphorus in the denominator. I want atoms in the numerator to get me to where I want to go. The relationship here, 1 mole is equal to Avogadro's number. .022 times 10 to the 23rd atoms for every mole. So 3 times 10 to the negative 10th multiplied by Avogadro's number to one significant figure, because we only started with the one here, would be 2 times 10 to the 14th atoms of phosphorus for every mole of silicon. All right, any questions with this particular example? All right, let's jump ahead then to another example. The ionic compound calcium carbonate is the active ingredient in a popular antacid tablet. That antacid tablet would be Tums. How many moles of calcium carbonate are in a tablet with a mass of 502 milligrams? And then secondary question, how many formula units are there? So let's answer A for right now, and then we'll start our discussion Friday with B. So 502 milligrams of calcium carbonate. So the first thing we want to do is we want to convert that milligrams into grams. There are 1,000 milligrams in every gram, so my milligrams will cancel. Now to go from grams of a substance to moles, I'm going to need to divide by the molar mass. So from a dimensional analysis standpoint, grams of calcium carbonate go here in the denominator, moles, calcium carbonate here in the numerator. 1 mole of calcium carbonate, molar mass of the substance, I need the mass of calcium, which is 40.08, plus carbon, 12.01, and oxygen, 16 times 3 to 2 decimal places. And 2 decimal places is kind of the standard number of decimal places to carry out of a molar mass. We get 100.09. Why 2 decimal places? Relatively simple reason is we don't want our molar mass value off of the periodic table to determine the number of significant figures. Since the periodic table usually gives us several sig figs, we want to make sure that the measurements are dictating sig figs, not something that's precisely known, like the mass of an atom. So 502 divided by 1,000 divided by 100.09 to 3 significant figures would give us 5.02 times 10 to the negative 3rd moles of calcium carbonate. So that is where we will leave it for today. We'll come back on Friday and finish this up. I'll give you a chance to review a little bit there as well. On your way out the door, you know what I want from you? Let me know where you are. How you feeling? And again, if you're answering in the red or the yellow, let me know where you're struggling, where it can be easier in that top hat Buddy's point question. Because at the very least, I can give you some resources to help you get unstuck if that's where we need to be. But that's all for today. Have a great day. I'll see you on Friday.